The previous videos in this series described how analog television works. However, in the UK, digital TV was progressively introduced between 2007 and 2012, and in 2012 the analog TV system was switched off. This video is a simplified explanation of how digital and flat-screen television systems work. You may wish to watch the two videos How Television Works Part 1, Monochrome TV, and How Television Works Part 2, Colour TV, before watching this video, as we will use some of the basic concepts described there to explain how digital TV works. For many years, there had been a drive for higher definition television with wide and large screens like cinema, but this was not possible with analog technology, and cathode ray tubes, which would have been massive and heavy. However, the rapid advancement in digital electronics and flat panel technologies have made it practical. Digital TV also enabled high-definition television, and in addition, digital channels take up less bandwidth, so that broadcasters can provide more channels in the same space. They can also provide other services such as multi-channel audio and electronic program guides. In the How Television Works Part 1 video, we explained how early monochrome TV worked, including scanning, line and vertical sync pulses. This picture shows the appearance of a video signal where the amplitude represents the light intensity, and it also shows examples of vertical and line sync pulses. Digital TV technology is built on this system. To create the colours of the spectrum, it is possible to combine different amounts of red, green and blue at different intensities. This slide shows 3 blocks of light, red, blue and green. If we add red light to green, we create yellow. Similarly, if we add red and blue light, we create magenta. If we add blue and green light, we create cyan. Finally, if we add red, blue and green, we can create white light. By varying the depth of colour, known as saturation, then a wide range of colours can be produced. In the How Television Works Part 2 video, we explained how analog colour television works. We showed an example of a luminance signal Y for a single line, for example when scanning a grayscale, as shown here. The dark portions of the image are a lower voltage than bright portions. The luminance signal is the same as the video signal in the black and white system, and it contains the detailed information in the picture. This shows the colour difference signals R-Y and B-Y, and what these look like when scanning a set of colour bars as shown here. The colour signals do not need to contain as much fine detail as in the luminance signal, because the rods in the eye detect the fine detail in the image compared to the lower resolution of the cones. Finally, we explained that green is obtained by subtracting R and B from Y. So you can see that the R, G and B signals for the colour bars are shown from white to yellow, to cyan to green, to magenta to red, to blue and finally to black. In digital TV, the 3 signals, luminance Y, and the 2 colour signals R-Y and B-Y, are converted into 3 digital data streams before compression, encoding and subsequent transmission. Broadcasting of digital television signals involves 3 steps. Digitisation, which is the process of converting the analog video and audio signals into a series of bits using an analog to digital converter. Compression, where the digital data is modified to reduce its size. And encoding, where the digital data is converted into a stream of bits that can then be transmitted. Each of these processes will now be described. Digital television uses a digital signal instead of an analog signal to transmit programs. Information in a digital signal is transmitted as ones and zeros, binary bits, which are put back together at the receiving end to form the picture and sound. This picture shows an analog signal. Below this is a digital signal where the amplitude of the analog voltage is converted into a series of ones and zeros. There now follows a simple explanation of how an analog signal is converted to a digital signal. This shows a simple example of an analog signal varying in amplitude over time. The analog signal is converted to a digital signal by measuring the value of the analog signal, which could be a video or audio waveform, at regular intervals. In order to convert the analog signal into the digital domain, it's measured periodically at the sampling frequency, with the sample values being stored as binary numbers. When the amplitude is sampled, it is rounded up or down to a discrete value called a quantization level. Each of these levels is represented by a binary number. When the amplitude is sampled, it is rounded up or down to a discrete value. In order to accurately sample an analog signal, Nyquist's theorem states that a sinusoidal function in time can be regenerated with no loss of information as long as it is sampled at a frequency greater than or equal to twice per cycle. For standard definition television with a video bandwidth of 6 MHz, a sampling rate of 13.5 MHz is used. For high definition television with a larger number of pixels, the sample rate is 74.25 MHz. If we convert an analog TV image to digital, then the picture is made up of a number of small picture elements called pixels due to the digitisation process. If we zoom into part of the image, we can see the individual pixels. Here you can see the individual pixels. You can see how adjacent pixels are rounded up or down according to the quantization level. The number of quantization levels were chosen so that at normal viewing distances, the pixels cannot be seen by the naked eye. The choice of the number of bits per signal pixel influences the data rate of the digital TV signal. Visual experiments were carried out to determine the number of pixels to reproduce a monochrome grayscale signal. The number of bits were increased until no contours were visible on the monitor. This resulted in a figure of 8 bits per pixel. So 2 to the power 8, or 256 quantizing levels, were chosen for transmission on terrestrial TV and DVD. Color TV broadcasting involves the transmission of 3 components: luminance Y and 2 color difference signals called chrominance signals. CR represents the R minus Y signal, and CB represents the B minus Y signal. Each of these signals are fed into an analog to digital converter circuit, or ADC. The 3 signals are independently sampled and converted into 3 digital data streams. The luminance signal carries the most detail, as was explained in the How Analog Color TV Works video. For standard definition pictures, the maximum frequency is about 6 MHz. This needs to be sampled at a frequency greater than or equal to twice per cycle, so a sample rate of 13.5 MHz is used to capture all the detail. The eye is less able to see detail in colours, so the chrominance signals are sampled at half the rate, at 6.75 MHz. The 3 digital data streams are then combined in a multiplexer circuit, which produces a single data stream with a total sampling rate of 13.5 plus 6.75 plus 6.75 MHz, i.e. 27 MHz, which is known as the system clock. As we explained earlier, 8 bits are considered to be adequate for standard definition television and DVD. Bit rate equals number of samples per second multiplied by the number of bits per sample. The number of samples per second equals the number of samples per picture times the number of pictures per second. For a 625-line raster standard definition television signal, 576 lines are used for the visible part of the image, and there are 720 pixels per line. Therefore, the number of samples for a standard definition digital television picture is 720 times 576, which is 414,720. For a picture rate of 25 per second, the number of samples per second is 720 times 576 times 25, which is 10,360,800. So the bit rate for the luminance component using an 8-bit code is 8 times 10,360,800, which is 82.944 megabits per second. The chrominance bitrate is half that of the luminance, which equals 41.472 megabits per second, but since there are two chrominance components, the total bit rate is 82.944 megabits per second. So the total video bit rate is 166 megabits per second. To be able to use the existing UHF transmitters in the UK, a bandwidth of only about 8 MHz is available. In order to transmit the digital video and audio signals, the data needs to be compressed to reduce the data rates. In addition, digital television needs to be able to carry more than one television channel per transmitter. This means a compression ratio of about 50:1 is required for standard definition and significantly more for high definition television. There are two types of compression, lossless and lossy. With lossless compression, all of the data in a file remains after it is decompressed and all the information is restored. Lossy compression reduces a file by permanently eliminating some information. When the file is decompressed, some of the original information is lost, although it may not be noticeable. For digital television, lossy compression is used. A series of techniques have been developed to reduce the bit rate of the digital video signal, and these are incorporated into standards under the umbrella term MPEG. MPEG stands for the Moving Picture Experts Group, and is an alliance of experts from industry and academia who work together to create a set of standard definitions for use for video compression. There are two MPEG standards that apply to digital television: MPEG 2 for standard definition television and MPEG 4 for high definition television. The MPEG compression process is extremely complicated, but the basic process is explained as follows. Video compression makes use of two features of video. Since the video is a succession of still images, it is possible to compress each frame in the same way that still images are compressed. This is known as spatial intra-frame compression. The second feature is that in general, successive images of a video vary very little unless there's a lot of movement in the video, making it possible to dispense with the unchanging or redundant part and send only the difference. This type of compression is known as time-related interframe compression, or temporal discrete cosine transform compression, DCT. Spatial intra-frame compression works by changing the color values of pixels and blocking together groups of pixels with more uniform color, so that it doesn't have to store as many different ones. While this does decrease the image data size, it also alters the color slightly, but the amount of compression is not noticeable to the viewer. If we zoom into part of the image to see the individual pixels, you can see the individual pixels made of blocks of the same color, thus reducing the amount of data needed. Intraframe means within a frame, so if intraframe compression were to be the only compression technique used, then each frame would be encoded individually. Unfortunately, this does not provide enough compression to enable the digital signal to fit within the 8 MHz bandwidth available, so additional compression is required. This is obtained by a technique called interframe compression. In this case, we transmit one complete frame, called an iframe, for a group of several frames, and then we only need to transmit the parts of the frame that are different from the first frame. Here you can see one frame from a video sequence. When we move to the next frame, you can see that only certain parts of the picture move. A movement predictor is used to identify possible changes from one frame to another and only encodes the changes for the next frame. For example, in this case, much of the picture is static and only the presenter's mouth is moving, so the movement predictor only encodes these changes. From this, a group of pictures is created. The first picture in a group of pictures is an intraframe or iframe. An iframe is encoded using only information from within that frame without reference to any other frame. Some following frames, called predicted frames or P-frames, are then generated from the information in the iframe and the changes generated by the movement predictor. Iframes and P-frames are categorized as anchor frames, and these are used as references to create more frames. Additional frames called bidirectional frames or B-frames are then generated by referring to the preceding and subsequent anchor frames. The next group of pictures again starts with an iframe and so on. MPEG-2 compresses the video bandwidth down to the required 4 megabits per second, which enables standard definition video to be transmitted in less bandwidth than is needed for analog TV. MPEG-4 is a more advanced compression standard which is used for high definition video, and this reduces the size of a high definition video signal down to about 15 megabits per second. The actual compression process is very much more complicated than described here, but this demonstrates the basic principles. For comparison, uncompressed high-definition television bandwidth is about 3 gigabits per second, and 4K ultra-high-definition TV bandwidth is about 12 gigabits per second. Audio analog left and right channels are digitized into digital binary codes by quantizing in a similar way to video digitizing explained earlier. The digital signal is also compressed using a variety of techniques such as Dolby to remove information in a way that's not detectable by the human ear, but enables the digital signal bandwidth to be reduced significantly. In this case, the compression is performed by using an MPEG audio encoder. The basic components needed for digital TV transmission are described in this block diagram. The video signals, luminance and chrominance, are sampled in an analog to digital converter or ADC as previously described. The video signals are then encoded in the MPEG video encoder, and the output is called a packetized elemental stream or PES. The audio left and right channels are also sampled in another ADC and are then encoded using the MPEG audio encoder to produce the audio PES. In addition, service data, for example subtitles and electronic program guides, are generated in digital form, so they require no encoding and are produced as a service PES. This information is then combined in the transport stream multiplexer, which produces a stream of data called the transport stream. The transport stream can then be used to modulate the transmission carrier, and this can then be transmitted via a terrestrial transmitter or satellite. The modulation scheme is very complex. It uses a technique called coded orthogonal frequency division multiplexing, COFDM. It is beyond the scope of this video to describe COFDM in detail, but the important feature of this technique is that it spreads the signal energy spectrum evenly across the bandwidth of the channel, rather than the peaks and the concentrations that occur in an analog TV signal. This results in a considerable saving in transmitter power. The key features of COFDM are: it encodes digital data by dividing it into multiple closely spaced subcarriers. Each of the subcarriers are transmitted simultaneously using a modulation technique called quadrature amplitude modulation, or QAM. Each subcarrier carries bits from the incoming data stream, allowing multiple bits to be transmitted in parallel. It copes well with severe channel conditions such as attenuation, interference, and especially multipath propagation. Quadrature amplitude modulation conveys the data by modulating the amplitudes of two carrier waves of the same frequency which are out of phase with each other by 90 degrees, a condition known as orthogonality or quadrature. The transmitted signal is created by adding the two carrier waves together, and this is a very efficient process for transmitting data within a given bandwidth. The UK Freeview channel, for example, used 64 QAM, in which the carrier wave can exist in one of 64 different states. There now follows a description of how the digital colour television receiver recreates the image. A signal from the transmitter is received by the TV's antenna. The tuner selects the channel, and a demodulator extracts the digital signal. The demultiplexer extracts the video and audio streams and the service data stream. The decompressors then reconstruct the uncompressed digital audio and video signals. The digital video signal is then passed through a digital to analog converter to then produce the video luminance and chrominance signals. These are then dematrixed to produce the R, G and B signals to drive the display. The digital audio signal is passed through the digital to analog converter, which produces the analog audio signals to then be amplified and reproduced through the loudspeakers. In recent years, flat panel technologies have replaced the cathode ray tube technology that was described in previous videos. There have been various technologies used, including plasma screens, liquid crystal displays, LCDs, backlit with fluorescent lamps, LCD LED screens where the backlight was light-emitting diodes, and more recently OLED, organic light-emitting diode, in which the emissive electroluminescent layer is a film of organic compound which emits light in response to an electric current. Most TV screens at present are either LCD or OLED. With an LCD television, all of the pixels are illuminated by an LED backlight. With OLED, each pixel provides its own illumination, so there is no separate backlight. Currently, LCD screens can be brighter than OLED screens, but are not able to reproduce a pure black level. LCD screens are also cheaper than OLED screens, but OLED prices are reducing with time. Before you can understand an OLED, you need to understand how conventional LED works. You take two slabs of semiconductor material, typically silicon, one slightly rich in electrons called N-type, and one slightly poor in electrons called P-type. The N-type and P-type slabs are then joined together. Electrical contacts are fitted to the two slabs of silicon. If we connect a voltage source, for example a battery, via a resistor to the two contacts, then electrons can flow through the junction from the N-type side to the P-type side through the circuit. This happens because the electrons more easily flow out of the N-type side of the junction and more easily flow into the P-type side. Electrons are subatomic particles and are far too small to be seen in practice, but are represented in a diagram by red dots. An electron hole is one of the two types of charge carriers that are responsible for creating electric current in semiconductor materials. A hole can be seen as a space evacuated by an electron. Unlike an electron, which has a negative charge, holes have a positive charge that is equal in magnitude but opposite in polarity to the charge of an electron. Holes are represented here by white dots. Holes can move from atom to atom in semiconductor materials as electrons leave their positions. An LED is a junction diode with an added feature. It makes light. Every time electrons cross the junction, they release surplus energy and give off light. OLEDs work in a similar way to conventional diodes and LEDs, but instead of using layers of N-type and P-type semiconductors, they use organic molecules to produce their electrons and holes. A simple OLED is made up of 6 different layers. The top layer is called the seal, and the bottom layer the substrate. In between those layers, there is a negative terminal called the cathode and a positive terminal called the anode. Finally, in between the anode and cathode are 2 layers made from organic molecules called the emissive layer, where the light is produced, which is next to the cathode, and the conductive layer next to the anode. When a voltage is applied between the cathode and the anode, then electrons enter the cathode and holes enter the anode. The electrons then enter the emissive layer and the holes enter the conductive layer. The holes and electrons then combine and emit light. OLEDs can currently only produce white light. As we explained at the beginning of this video, we can make a range of different colours by combining red, green and blue light. So by making 3 OLEDs for each pixel, a colour filter can be placed in front of each pixel to create red, green or blue light. By varying the current through each OLED, the light intensity for each colour can then be varied and all colours can be produced from black, where the OLED is off, to white, where each OLED is on. Then by varying the current through each OLED, the pixel can be made to be any colour. The dimensions of each pixel are approximately 0.3 mm square. A matrix of OLEDs can then be made into a panel with 3 OLEDs per pixel. This is a close-up view of the OLED panel. A colour filter panel is then placed over this panel. Zooming out to normal viewing distances, the naked eye is then unable to discern the individual pixels. Finally, a glass screen is placed over the whole assembly to create a flat panel screen. Each LED can be individually addressed and the brightness of each colour varied as the current through the LED is varied. This then enables a raster scan to be produced to build up the picture in the same way as was described in the previous videos. Digital television and high-definition television, HDTV, are sometimes confused. DTV refers to digital broadcasting technology, while HDTV is an advanced digital broadcast format with higher resolution than standard digital broadcasts. SD, or standard definition, was the first format for digital TV. Then came 1080 resolution, often referred to as Full HD. This has 1920 by 1080 pixels and has become the industry standard for HD digital video. More recently, 4K resolution has become available. Also called UHD or Ultra High Definition Television, this has a resolution of 3840 by 2160 pixels. Finally, some TVs are now available that can display 8K resolution, which is 7680 by 4320 pixels, although as of today, in 2024, there is little source material available with that resolution. Recent TVs have featured high dynamic range, or HDR. The dynamic range refers to the range of brightness between the darkest area and the brightest area in an image. This graph shows the intensity of the light on the x-axis and the signal value on the y-axis. The red curve shows the signal value versus the light intensity for standard dynamic range. The curve is called the gamma curve. High dynamic range imaging refers to the set of imaging technologies and techniques that allow the dynamic range of images or videos to be increased. This means that there is a large amount of variation in light levels within a scene or an image. The blue curve shows the gamma curve for HDR, and this is called hybrid log gamma, and shows that the light intensity can be much greater than that for the SDR gamma curve. HDR enables it possible to see details in content in both very bright and very dark scenes. HDR signals send metadata to the TV, which is a list of instructions for the TV to display content properly. The source tells the TV what exact colour to display at which exact brightness level. The LEDs in the screen must be capable of producing the required range of brightness. HDR TV sets feature wide colour gamut. Gamut means the complete range or scope of something. This graph is called a CIE chromaticity diagram, which is a standard way of showing the colours that the human eye can perceive. The blue figures are the wavelengths of the pure spectral colours from 380 nanometers to 700 nanometers. The triangle shows the range of colours that an SDR TV can reproduce. The point marked D65 roughly corresponds to the colour temperature of the sky on a clear day around noon. A normal TV screen can only display a limited range or gamut, as shown by this triangle. A 4K wide dynamic range TV gamut is shown by this triangle. When compared to the SDR colour space, you can see that the HDR has a much wider range of colours. Cambridge is well known for being a high-tech centre with lots of innovative electronics companies. In fact, Pi could be considered to be one of the founders of that industry. Pi was named after William George Pi, who founded the company in 1896. It started as a small scientific instrument company, but it expanded into radio and all manner of electronics. The first British transistor radio, colour television was being demonstrated in 1949 and was actually used at the Queen's coronation in 1953. So it was a world leader in a great many of these technologies. So it was particularly important for us to create this exhibition to show people what Pi did. And it was very appropriate that it should be at this museum. The museum already had a number of Pi items in their collection. This exhibition covers all aspects of Pi with examples of the products and the history of the company. This is the perfect location because we're on one side of the river and on the other side is where Pi's main factory was. So it's a very good place to be.